challenges related to fabrication, related to solidification, related to the quality aspects. And so we will see that when we started having the fabrication of this metal matrix composite material, there itself there was challenge regarding the homogeneous distribution of reinforcement particles. Now the challenge was that if you have a metal matrix composite material in the form of plates, now there was always challenge to cut it. So you know that cutting is again a challenge, welding is a challenge, forming is a challenge, and mostly we have the use of such materials in the aerospace applications or in the automobile applications, and there in most of the cases you require the material to be in the form of sheets or small thickness plates, and you know that either you can form it for making less thick materials, or you have to cut it. Cutting is normally very challenging because plate itself being about maybe 6 to 7 mm thick plate you are making by casting method. Cutting, thickness wise is difficult because one is how to cut it, another is again after cutting you don't have a finished surface. That too you have embedded matrix material, that poses another challenge. So that's why when I was using the composite material, using continuous casting process, we thought of making composite sheets itself using continuous casting. Although by that time, the development of continuous casting was already applied to normal materials like steels and aluminum-based alloys, on which we had presentation by Professor Dhinda yesterday. So we thought of having the material using continuous casting route, and that's why one of the students who was his student also at one point of time, we thought of having a setup to make the continuous cast metal matrix composite sheets, and I will show you some of the work because that work got some patent from our side. I mean, we applied and we got it. And so now why we call it as a sustainable manufacturing approach, because in this case, as we know, there is minimum of wastage and large amount of saving of energy, because once you use continuous casting process with respect to normal casting, you have a lot of reduction in the wastage, like whatever wastage you have in terms of riser or casting yield improvement is tremendous. So as you see, if you see the background, there is a lot of emphasis on the green aluminum. Aluminum is one of the most widely used material, being lighter, and it has many applications. So there is a lot of emphasis on the use of this towards sustainable manufacturing, how we can contribute towards the environmental goals set by the government or as a whole in the world. And we are talking about having this processing, production, waste management. Then we have certainly, these are the methods where we go. And a lot of emphasis is there nowadays on recycling. Now, if you see the application of aluminum, you may know all that it's very much used in all the industries like automotive, space, and everywhere we use it. So what are the challenges? As I told you that when we are always going for any material, and if it's new, a process or a product, we have the challenges. And in case of metal matrix composite materials, it's very obvious, all of you know that the distribution is a very big challenge. In most of the cases, we have agglomeration because there is a lot of density difference, or there is a powder which is there which is lighter, so it will be floating, and you have to ensure that they properly go inside the melt. So the distribution is a challenge. Segregation will be there because of that. Size and shape. Yeah. So size and shape is another important thing, because once you are putting the powders, that will be acting as a nucleating agents. And in that case, sometimes if there is agglomeration, you have size of reinforcement particles will be non-uniform. And the shape also, many a times you get different shapes. Sometimes you get needle-shaped reinforcement particles, but you like to have a spherical shaped particles to have the better mechanical properties. Melting and handling. So in most of the cases, we try to have a simplified approach, although we know that when we deal with aluminum or magnesium, we need to ensure the presence of vacuum conditions because of very reactive nature of aluminum or magnesium. But in that case, we try to see that how can we minimize the presence of or the insurance of such conditions like vacuum, although it's a necessity, otherwise you will have the problems of porosity which we get. But we can certainly reduce the porosity by the application of the vacuum conditions. Flow control, thermal management, so these are externally you can do something, and you can also do CFD analysis to see their effect. Tooling die design oxidation is a challenge. So the thing is that if you are making through conventional route, you have a lot of steps which is required. You have to make a thicker sheet, and then you have to further cut it or maybe deform it or go under forming, which is to be avoided. If you see the fabrication processes, these are the processes which are used for the MMCs, and you can see that although it is there, but if you go for continuous casting, still particularly reinforced MMCs are not being practiced. So we tried to delve into this domain and tried to see that how can we get it. And particularly reinforced composite strips, you have a lot of advantages, and certainly all these methods have we have also used, but we will see that how can we do it through continuous casting. So for that, so this is something about the continuous casting. As you see that here you get these kind of sheets normally by a lot of routes, like if you are visiting the steel industries, you have hot rolling, cold rolling, and ultimately you are getting these strips. Now this is a typical schematic of continuous casting process where you have the metal coming from ladle to tundis, and then it is going through this mold. Normally this is mold for the slabs or billets or blooms, and that's the concept which is used for making even thinner sheets. So our objective was to develop a twin roll continuous casting setup for fabricating composite sheets, numerical model development for predicting the input parameters, which is because many a times you have to predict something. You know that the liquid metal will be flowing in between two rolls, and there is a large heat transfer coefficient which is going on. So the situation may be that it may stuck somewhere, or if it may come as in a liquid state itself down. So you have to have certain parameters, and in that case you predict it very betterly by using the numerical modeling approaches. You have to identify the challenges and issues while addressing the setup, because as I told you that these are how can successfully you get these strips, and you also assess its mechanical properties, microstructural evolution of the material. This was a setup which was designed, and this setup was using these two rolls. In between you are having the liquid metal from here, so this is liquid metal being poured, and then it will be coming up, and you have cooling mechanism from this side. The cooling liquid, that is water, is here, that will be flowing and it will be coming out here. So you can record the temperature difference between the incoming and outgoing water stream. So that way this was planned. A lot of calculations were done, and experimental work was, the patent which was awarded for having this strip, metal matrix composite strip, which was out of this work. So in this case, when we also developed numerical model where these assumptions, certainly when we do deal with numerical investigations, many a times we have to have certain assumptions to avoid some complexity. Certainly that induces some numerical errors, but many a times these numerical errors propagate, or they also cancel each other. You must be knowing that when we deal with numerical methods, we use meshing schemes, and certainly we are approximating them, but many a times you will see that they are very much close to the actual observation, And that is because the errors which are there, they cancel many a times, few things. So mostly it is for validation purposes. And that tells you that how close you are going and how many assumptions. I mean, practically you have to take those assumptions only which you cannot incorporate. Otherwise, you must incorporate all those practical assumptions in the model. So these are the governing equations where normally we deal with mass conservation, momentum conservation. And certainly when the metal is flowing, you have either a laminar flow or a turbulent flow regime. And you have models available for that, because ultimate aim is that how this viscosity is going to be affected, how the viscosity is changing. You have effective viscosity coming into picture, and you have laminar part of viscosity as well as turbulent part of viscosity. And you know that viscosity, why it is important. You have, viscosity is used because you know viscosity. Once you know the shear stress, and then how it will be affecting those at the boundaries, those flows and all. So normally this low Reynolds turbulence models are used in those cases where you assume that the flow may be turbulent, and also in certain regions it may be laminar. So there are low Reynolds number available, and you can use them. They judiciously calculate those turbulent parameters like Y plus or so, and based on that Y plus values, they will be employing the favorable or the required Reynolds number or this turbulence model to calculate those turbulence parameters. And finally, you will be predicting the output parameters like velocity, temperature, turbulence parameters and all. These are the properties, thermodynamic mixture model. So you know that you have, once you are dealing with solidification, you have to deal with those conditions where you know that this machine zone will be there, how there will be properties changing. So you can have incorporation of those things, how there will be solid and liquid phases coming up. So at what stage there will be how much of solid is there, how much of liquid is there. So in that case you have porosity's determination is there, and then you can finally predict the temperature and other parameters. This is the properties which we have taken, like that will tell you about the materials and also about the rolls. So we have taken the material like Mg2Si, aluminum Mg2Si, which is very light, used for aerospace applications, and you have the temperature given. Near eutectic composition was taken. Yeah, so this is how the work started, and the modeling work also started. You have, I should not, please remind me when the time comes up. Now this was done, so there was a graphite mold, and in the graphite mold the metal was given. Now the thing was that when you start, finding the heat transfer coefficient is important. That what will be the heat transfer coefficient, and normally you give one heat transfer coefficient and you try. Now most of the challenges is that if you have improper heat transfer coefficient being taken, that will lead to, that will give you some result but not realistically correct. I mean, so for that we started with the three types of mold. One was using the graphite, another was with normal iron mold, and third was using the continuous casting. And then this graphite mold which was used, it was also used to find the heat transfer coefficient, because we tried to have the calculation of interlaminar spacing, because the metal which will go from the mold, it will be going through corners, and it will be leaving one section of material which is solidified in the mold itself. Based on that, we find the interlaminar spacing, and from that, using the constitutive relationships, we found what is the predicted heat transfer coefficient, and we found that with numerical work also, we got similar to that value. Okay, so this is what the heat transfer coefficient calculation was done. As you see, this was the portion which was unsolidified. This was solidified. Metal is going through that, having from here, we also had some criteria. Fs is 0.7, so that was the solidification criteria based on dendritic coherency point. It is assumed that when you have Fs of 0.7, you have the dendrites becoming coherent, and then that was the assumed, and based on this line, we saw the experimentally obtained things were, because we see that with this kind of heat transfer coefficient being chosen, it will be completely coming up at the nip of the mold, and the metal is coming out. So there were certain, you see that here, it's not getting solidified till this point. So your liquid metal will come out here. In this case, it is just solidifying at this point. And in this case, it is solidifying here itself. So it will lead to blockage at this case. So you have those, once you do that, you will get a value which should be used for successful fabrication of the sheet. Yeah. So further in that direction, this was again for the calculation. You can see that how it should come near that point so that it can come successfully. These were the results which gave us that how. Now the thing is that when you are getting, our aim is to have the material in a very homogeneous manner, or the uniform distribution of ceramic particles or these reinforcement particles, and that was seen that we were able to achieve that. This is the lamellar spacing which was calculated based on certain relationship which was suggested by the authors in the past. As we see that using the simulation, we had got this range using the hybrid approach, and this is a lamellar spacing approach. With the three approaches we got, and we got that, although there were some standard deviations here and there, but then we got that 1350 was the enough one for giving us a quality sheet. So these were also used, that how you did the superheating. Now I told you that when we do the superheating, superheating means metal will go past this place and it will coming up as a liquid, and when you decrease the temperature, it will choke here itself. So you can do the numerical modeling to ensure that, and accordingly you can adjust your casting temperature. This was the sheet. As I told you, that in this case you are getting the metal which is coming up in the liquid form, and ultimately you have successful ones. So with the successfully you got with some velocity of the roll. Now there are many parameters. If you are conversant with the continuous casting thing, you have many things like temperature of the metal, velocity of the roll, and roll gap. Lot of things are there. You can do lot of calculations. You can do work on that and see that how they can optimally be varied to give you a successful combination of parameters and also the sheet. So these were the experiment which was done by students, and we'll move forward. So as I discussed with you, you have all these results which gives you that how can you get. These are the, so you can see that very uniformly you are getting the composite material with reinforcement and presence of all these. Now you get certainly some shrinkage, some porosities are there. Porosities are available because we are not using the vacuum conditions, and if you use the vacuum conditions, then certainly these porosities are likely to be very, very less. So these porosities need to be removed in our future efforts. You are getting some centerline shrinkage, and as we are here in this, certainly you must have very much idea about the shrinkage which you get. Normally it is towards the center because of the solidification pattern which is moving from sideways, goes inside. So certainly your shrinkage normally you will be getting mostly towards the center line. So certainly we need to improve the mechanical properties because of the porosity, and we need to have the emphasis on the processing at parameters and control atmosphere, and also we did the rolling of that material at some temperature to ensure that we can further reduce its thickness. You know, when we had the plates, we thought of rolling it, but when we used sheet itself of 2 to 3 mm, no need of going for rolling. These are the factors which we have to see. This is swot diagram which will tell you that what are the factors which we need to look into. One of the another thing which we tried was the delivery of metal from certain height many a times, and that will be affecting this porosity which we got. So porosity can be improved, as I told, that you can do the work initially by modeling, and then you can further do the work. So such setup, what I mean to say, that you should think of having the setup. Setup is not very costly. If you think, you can have a setup and you can try. So ultimately we did with this melt pool height, and we got few results with that also. We saw that how we are getting with what melt pool height, how you need to adjust your melting point or the pouring point of pouring temperature of the metal, so that you get optimized sheet. These are some of the intermediate results. We will move forward. Few things which we saw, that there is a lot of porosity changes, and you see that how we changed the melt pool height from 4 to 8, and see the difference in the porosities levels. So that is changed because of electrostatic pressure from the top, maybe that was the reason. These are